Welcome back everybody. We're going to look at some circle geometry in proof, and the three proofs or the three theorems we're going to look at are useful if we're trying to find information about angles or just trying to determine angles. So there's three theorems here, but theorem 1 is the pivotal one. The other two rely on theorem 1. And just to note, some books or sources or whatever, videos, so on, will give these theorems different numbers sometimes. So this is the theorem 1 according to me, but other sources may differ in the number they associate with this theorem. So here we are, the theorem 1. The angle at the center of the circle is twice the angle at the circumference subtended by the same arc. Now, in a previous video I've gone through all the terminology regarding circles, so please go back to that earlier video, especially the word subtend. And so you can see that we've got a diagram there, and we also have a little symbol. So whenever we refer back to this theorem, once it's been established, we can use that symbol to refer back to it. Okay, so you can see a diagram here, and basically if the magnitude of the angle at the circumference is x degrees, then the magnitude at the angle at the center, alright, this corresponding angle here, is twice x. Okay, and that's what we're going to prove. Notice how they're both subtended by this green arc. Okay, so in the proof, the first thing I'm going to do is put in a diameter, and I'm going to label this point here D. Okay, and I've gone over O there. You remember that O was there, so that's our first step. I've noted here that there is an angle X and an angle Y. So angle X at angle CAO and angle Y at angle BAO. Okay, and so we can note that this will be important in a little while, this information. So CAB is the sum of angle X and angle Y. So that'll be useful very soon. Okay, now you might have noticed too, I put some notches in there indicating the same length. So where that comes from is from this statement here. So since OA equals OC and OB, we have two isosceles triangles formed. Okay, you can see them on the left there. There's CAO, and there's also a CAO, and AOB is the other one. So we're going to consider AOC or CAO, whatever you want to call it. I will call it the triangle AOC. So consider triangle AOC, and we'll let angle CAO. Okay, so you're going CAO equal X as we did just above, and angle ACO will also equal X because of the isosceles triangles. Okay, why are they isosceles triangles? Because they're the radii of the circle, which is a constant. Okay, all right. So also we have angle DOC. Okay, so DOC, that angle there. Now, because of the property external angle equals the sum of the two internal opposite angles of a triangle, we can say that DOC, this angle here, equals that angle plus that angle there, which is X plus X. Alright, and because they're the same, we can add them together. They're like terms, 2x. Similarly with triangle AOB on the right hand side there, just quickly looking back in case you've forgotten, AOB, that triangle there, AOB, we said let angle OAB equal y. We said that a little bit earlier on. Okay. Angle BAO will also equal y because of the same reason given before. With the other side, we have isosceles triangle because of the two radii. So we can put that little isosceles symbol there. Angle DOB at the bottom because of the external angle equals the opposite two internal angles summed together in a triangle. They will equal, we've got BAO plus OAB, so BAO plus OAB, triangle OAB, that's a triangle symbol. Sorry, little error there, that's going back a couple of lines. It should be OBA, sorry, angle OBA. Otherwise I would have had two, I'm talking about the same angle twice. Alright, so that's OBA, and thus that needs to be saying OBA there. Okay, OBA. So we've got y plus y, which equals 2y. Okay, now remember before we said that CAB, the angle up the top there, and remember its importance to the proof is this angle up here. Whatever it is, whatever letter you assign, and by the way, the x means something different down here, that the value of that angle up the top, no matter what letters you use, is, okay, CAB, that angle, is x plus y. Down here we found an angle down the bottom here, or we're finding an angle down the bottom here. Alright, so once we finish doing that, so that angle at the bottom will be COB. Okay, so COB, it's that angle at the bottom, i.e. this angle here. We can show now that it is twice, and therefore we've proven the theorem. Okay, so here we go. We've got angle COB is the sum of angle DOC plus DOB, which we have is 2x plus 2y. Just from the results you can see a few lines above. Okay, so they're 2x plus 2y, which is 2 outside of x plus y. And remember, that is twice the angle formed at the circumference, which was angle CAB. So that's pretty much showing it now. So therefore the angle at the center is twice the angle at the circumference when subtended by the same arc. Theorem 2 leans on Theorem 1. Theorem 2 says the angles at the circumference subtended by the same arc are congruent. Okay, it has this little symbol here on the side, and it's saying more specifically if the magnitude of the angle at the circumference is x, then the magnitude of any other angle at the circumference subtended by the same arc, alright, there's an example, is also x. So you get this phenomena here. Okay, and we are going to apply Theorem 1 to support this. So let's suppose that both angle CAB and COB both stand on the ends of an arc. Alright, the ends of the same arc, which is CEB here. Okay, let's have a look at that. So there's CEB. Alright, now the point E there is so you don't go around and use the other complementary part of the circle. Yeah, okay, so CEB is the arc. Okay, so angle CAB. Alright, so let's have a look at that CAB, that angle, and COB there. They got ends. Look at that one's got that end. Yep, and CAB2 they both connect to the same arc CEB. Now, from Theorem 1, from just before, which was this one, two times angle CAB matches COB from the theorem we just did, number 1. Okay, we'll call that statement 1, and similarly we can say that 2 times angle CDB, so CDB equals angle COB because of the same reason. Okay, they both have ends subtending this arc. Okay, subtended by the arc. So if A equals C and B equals C, alright, we got A equaling B, a bit of logic there. So we can say angle CAB is equal to angle CDB. So in conclusion, angles at the circumference subtended by the same arc are congruent, or they're the same. Okay, the third and final theorem. Theorem 3, the angle in a semicircle is a right angle, alright? Or we could say it more precisely, the angle subtended by a semicircle is 90 degrees. Okay, there's its little symbol, and again we're going to use Theorem 1 to support this. Okay, and there we have a diagram showing the semicircle subtension, and then we've got the place where the 90 degree / right angle is. Okay, so let's get in and prove this final one. Okay, so a bit like what we did a little bit ago, suppose angle, in this case ABC and AOC, both connect to an arc. Alright, we're going to use arc ADC. So we got arc ADC, again D's a helper point, so we know which arc we're talking about, that arc there, and angle ABC. Alright, that was the one that was the right angle in the theorem. We're going to prove it here, so we haven't said it's a right angle, we just said some angle, and it's subtended by that arc, alright, semicircle. And AOC likewise, AOC is the straight angle here. Okay, so now ADC is it happens to be a semicircle. That's where it links to the theorem. Special sort of arc called a semicircle, right? And we also know that angle AOC, right, AOC through there is a straight angle. Now straight angles are a 180 degree angle. This is all important for reasons you shall see in just a moment. Oop, didn't mean to write plural there. Okay, now again from theorem number 1, we'll have 2 times the angle ABC will have to equal angle AOC. Now AOC is 180 degrees as we just established, so 2 times this angle ABC must be 180 degrees. So angle ABC is 90 degrees, therefore it's a right angle, no matter how you say the theorem. So essentially that's proven. Okay, we've proven the theorem, and the angle subtended by a semicircle is a right angle QED. I hope that helped, and you know, circle theorems might seem a bit dry at first, but you roll your sleeves up, get immersed in it, and you get to like them a bit better. So again, I hope that helped you out. Have a nice day.